Okay. Hi, everybody. I am Elisa Ferrari, and I have nothing to disclose. Okay, today I'm going to present you my research about common pitfalls in machine learning application to multi-center data. So the main subject of my speech will be the application of machine learning techniques in medical imaging. And why do we use machine learning in that field? Well, usually to discover difficult patterns in the data. For example, in my job, I'm trying to train a classifier to distinguish between subjects affected by autism spectrum disorder and typically developing controls from their MRI scans. And of course, the aim of this practice is understanding the decisional patterns discovered by the algorithm, and from that, finding possible biomarkers of the disease. But as in every medical imaging application, since we don't have enough data, we usually work on data collected by multiple centers. So we have data acquired with different acquisition parameters and different scanners. So the question that I want to answer during this speech is, how much will the biomarker that I'm going to find be affected by the bias introduced in the training data by the side effect? Okay, the problems that occurs in confronting images acquired with different modalities are well-known problems in literature. So my problem is subtler. I want to know how much my analysis will be affected by the side effect, not when I'm confronting the raw three-dimensional data, but when the data under study are obtained with a process involving lots of different steps. For example, a segmentation process followed by a feature selection, normalization, and so on. So I want to know if even after all these additional steps, the data still depends on the acquisition side. And this concern is even more important given that we usually presume that the data extracted with a segmentation pipeline are more abstract and reliable. And this is even confirmed, for example, for FreeSurfer by some publication. So to test how the data depends on the site after segmentation, feature selection, normalization, and so on, I have taken some data from an open repository, Abide, and I have trained some classifier to distinguish between the feature vectors belonging to two different sites. And as we can see, the data acquired with different acquisition parameters and different scanners are perfectly distinguishable in terms of AUC. But even the data in red acquired by the same site, so with the same acquisition protocol and the same scanner model, but not the same physical scanner, or maybe acquired in a different year, are pretty distinguishable. So that means that even the change of a coil or maybe an update in the software have a strong impact on the analysis. Okay, so now you could say to me that, okay, I've proved that data coming from different sites are different, and this was quite obvious. But what I want to understand is how my analysis is affected by side effect when I'm trying to find a pattern between two classes that are supposed to be really different. So let's take an easy task and let's forget about psychiatric classes. And let's try to distinguish between female and males. Okay, if I train a classifier and I validate it on data coming from the same site, I will obtain an AUC of 0.82. If I maximize the differences, taking all the females from one site and all the males from another site, I will obtain a mean AUC of 0.99. But what happened in the worst possible case ever, in which I have, in the training set, females coming from one site, males coming from another site, and I'm switching the site provenience in validation? Will the algorithm learn the differences due to the site or the differences due to the sex? Okay, of course, it will learn the best separation direction, and in this case, it is the site. And it's clearly visible because the AUC is 0, and that means that switching the subject in validation, we will obtain an AUC of 1. So we have proved that even in a very, very easy task, like distinguishing between female and males, the algorithm is pretty confused by the side effect. So now we want to understand if the differences due to the site are localized in specific features with a univariate analysis. So I have taken the data from one big site. I have subdivided the subject in 2 matched groups, and for every subject, I have extracted a feature vector long 420 features. Then I have done a mean operation across the 2 subgroups, and finally, the normalized difference between these 2 mean vectors is plotted in the blue line. And the light blue band represents the standard deviation in the original site A. So if I repeat this operation, taking the data from 2 different and matched sites, we obtain the orange line. And as you can see, the orange line stays always between the light blue band. And that means that the differences due to the site effect on a single feature are not much stronger than the natural variability across one single site. So in a univariate analysis, it's very difficult to detect the side effect. So at this point, my hypothesis was that the algorithm was very sensitive to small differences across all the 420 features. And I was interested in understanding how much should I reduce the number of features under study to eliminate the side effect. So I've taken the data from 2 different and matched sites, and I have extracted, as always, a feature vector for every subject. But then I have taken in consideration, I'm choosing randomly n feature for every classifier. So just to be clear, those dots represent the mean AUC of 100 classifiers trained with 100 different combinations of n features, and they are trained to distinguish between subjects belonging to state A and state B. And as you can see, my initial hypothesis was wrong because the classifier is able to perfectly identify the site provenience even with only 10 features. So that means that the differences due to the site follow a logic that is easily detectable by a machine learning algorithm. Okay, just to conclude, the dependence from the acquisition site has a strong impact on a multivariate analysis. And this is not limited to the scanner parameters, but also involves the specific scanner model and its eventual updates or hardware modification. And what are the possible solutions? Well, during that analysis, we can develop new deep learning methods that specifically try to avoid learning from the side effect, for example, using adversarial learning. And during the acquisition, well, we should use more quantitative signals as the promising magnetic resonance fingerprinting. Okay, thank you for your attention.